When we read about drones in the news, we perceive them as big, scary, expensive, and very likely lethal. But this is not what we will be talking about today. We will be talking about the small, the affordable, the sometimes odd, and sometimes also quite big. I'm also only interested in drones that adhere to the same ideal of freedom as freedom of speech. And some of those that everyone could build if they had a minute to spare. I know this is quite a problem for many of us. Also, I think a drone needs to be able to fly by itself. At the most simple level, the only thing that one has to tell the aircraft is where to go and what route it should take to get there. These flight instructions can be greatly more sophisticated than that. So where are we now? Almost all open source autopilot systems of today, like ArduPilot, OpenPilot, and Paparazzi, support fixed-wing airplanes in many configurations: a single engine, twin engine, flaps, ailerons, elevators, flaperons, elevons, and so on. Multicopters, not only quadrocopters, by a laundry list of different configurations, similar to airplanes, but even more so, 3, 4, 8, 12 motors in X plus over and under configurations. It is quite overwhelming how many possibilities this approach provides. Basically, attach a few motors with propellers to a bunch of struts, and you will probably be able to make it fly. Helicopters started the whole open source controller story, but to be honest, since the dawn of the multicopters, they do not seem to be the most common choice for conversion into a drone. The main reason is the cost of operation. The helicopter has a lot of very intricate mechanical parts that are expensive to manufacture. And if your software screws up and you crash, the fun becomes quite expensive very quickly. They are still being used in situations where you need a long flight time. It is easier to put together a turbine or combustion engine-driven helicopter than a multicopter. Recently, though, very cheap, very small helicopters have become available from China, making the helicopter an interesting platform again. More on that later. A new category of vehicles called transitioning vehicles is emerging. This is a combination between a fixed-wing aircraft and a multirotor. Transitioning vehicles take off vertically, can hover, and on a flip of a switch or a software command can transition into a forward flight, making it quite more efficient. This can be also achieved by tilting the engines themselves and not the whole vehicle. As far as I know, Paparazzi is the only platform so far that supports this new aircraft class in the vanilla codebase, including autonomous flight. But other projects seem to be catching up slowly. Many projects used Atmel or PIC microcontrollers, 8-bit architecture and 16 megahertz clock, or even worse, Arduino. But now, most of the projects are using ARM 32-bit processors that provide enough processing power to do some fun stuff without the programmers having to be code extortionists. This enables us to think about adding real-time OS for managing processes, for example, and encryption to the telemetry links, run more sophisticated estimation for more accurate control, or run intelligent path planning algorithms. The sensors have come quite a long way as well. For the last few years, thanks to the ongoing development of cell phone technology, the prices of micromechanical sensors have dropped significantly so that they have become affordable. They might not be the greatest, but they are good enough for most applications. And instead of paying $30 per degree of measurement, we pay $6 for 6 degrees of measurement, or $13 for 9 degrees of measurement in a single chip. Even though there are many different boards, at the core they have converged quite a bit. What they differ in most is the size and what integrated features they have, like radio communications, video overlay circuitry, servo connections, and communication channels to sensors and actuators. Here is a sample of a project. Listed here is only an excerpt out of Paparazzi-supported autopilot comparison table. As you can see, there are plenty to choose from. On the software side of things, the feature that even the simplest systems with a GPS support provide is position and altitude hold, sometimes also called loiter. For hovering vehicles, this feature is quite obvious. The aircraft stays on a spot at a designated altitude. In case of an airplane, this means flying circles around a set spot. A simple extension to that feature is homing. When powering on, the aircraft remembers the coordinates as its home position. During the flight, at any time, it is possible to flip a switch or press a button that will make the aircraft fly straight back to that spot. It is a great safety feature and an aircraft saver for beginners as well as experienced pilots. For Follow Me, an operator is carrying a GPS receiver. And the aircraft then follows the position of the GPS receiver like a virtual leash. I have the feeling this feature is not fully explored yet. I can imagine using such a feature to convert the aircraft into my personal cameraman. When flying an aircraft equipped with a gimbaled camera, it is possible to tell the autopilot to point the camera at a specific point on the ground. This feature is used very often by reporters and filmmakers. Waypoint navigation is, in my opinion, the minimal feature that needs to be provided before a project can claim that they support autonomous flight. This means you don't steer an aircraft yourself using a remote control. Instead, you mark GPS coordinates on a map, and the aircraft can navigate between those points. An extension of the waypoint navigation are survey pattern flights. In this case, the operator marks an area on the map and tells the aircraft to fly a pattern that will cover the whole area. That is very useful when you are generating maps, surveying crop fields, searching or studying tree canopies in the rainforest, for example. Almost all systems support some kind of geofencing. This means that if the aircraft leaves a virtually fenced-off area, it is able to perform some kind of an emergency maneuver. Depending on the regulations or mission requirements, it can then try to fly back home, switch off the engine and drop to the ground, or stay put and gain altitude instead of continuing the mission. There is a lot of more mission actions that almost all mature projects support by now, but these are mostly static flight plans. And the conditions change, and if the conditions change, one has to have connection to the aircraft to perform in-flight alterations to the mission plan. An improvement on that is using dynamic flight plans. One possible dynamic flight plan solution is implemented in the Paparazzi platform. The first-class citizen of a flight plan is not a waypoint, but a block. Each such block, consisting of multiple stages, represents an action. The actions can be setting system variables, altering waypoints, executing autopilot functions, or performing a jump to other blocks based on the system variables. These variables represent either sensors or counters. This solution represents a domain-specific language in which one can implement a dynamic flight plan. Each block is statically compiled C-routine on the ground as part of the autopilot firmware. So the flight plan implementation is safe from accidental change in flight, but still can react based on conditions, providing flexibility without compromising code size, restrictions, and safety. A very similar system is implemented in the Gluon pilot too. Here I need to give them some props because they are saying on their website that it is exactly the way Paparazzi did it. The OpenPilot team is working on another solution that they are planning to release in the future. It uses a Python interpreter running on board the aircraft. that can manipulate the waypoints and probably also the flight vector. But we will see how that works when that feature is documented and released to the public. There are many more things that we already can do, but this is how far we've gotten in the past 10 years. Now, let's try to predict a little bit into the future, or rather, let me tell you what I hope we will be working on next. Let us start with a great example of what is working very well so far. Paparazzi Sumo is, for example, that I have here on the stage with me. It's the aircraft here. It has been used for quite a while now by meteorological research groups as a reusable weather balloon. With basic training, the researchers that never flew an RC airplane before can take the Sumo, launch it, and gather humidity and temperature and wind information in air columns. Thanks to the efforts of the people like Martin Müller, it has become a standard tool that is as important as balloons themselves. Based on that, I believe we will see more drones used as sensor platforms. For that, I hope we will see more people like Martin Müller who will make sure the solutions are standardized and deliver very repetitive results. On the other side of the spectrum, I was shocked to hear that a simple seeming competition, the Outback Challenge, is still unclaimed. The mission consists of taking off from a runway, flying to a field that is 9.3 kilometers away, searching a 7.5 square kilometer area for a bright yellow dummy, and then dropping a half-liter bottle of water, it's a bit bigger than this, to the designated position. This sounds like a very simple job, but since the first competition in 2009, the main prize is still unclaimed. Teams were getting very, very close, but not close enough to claim the main prize. I have been told that the main reasons why teams fail is because the rules and requirements of the mission are overly demanding. So let's hope that the big prize will be claimed this year. But this has been made clear that the civil-use drones are still very much in their infancy. Drone technology, as well as the regulations regarding them, are in a need of advancement in order to mature. There is still a lot of pioneering work to be done. One striking development is miniaturization. There are plenty of very cheap and whatever quality toys in this area. But I believe this will be a starting point for an interesting burst of innovation, just like XUFO did during its time. There are already a few of the first really cool open source projects emerging. For example, CrazyFly by BitCraze. It comes with all the basic 10 degrees of measurement sensors and their own custom radio that you can connect to your laptop. The API is very well documented and the source code is released under open source license. This makes the device very compelling to anyone interested in experimenting with drones from the comfort of their chair. People are already doing very interesting things with it, like controlling it using Microsoft Kinect or adding sensors so it bounces off the walls without touching them, or adding their own 3D printing custom parts to the airframe. I think we will be seeing very cool stuff emerging based on this project. Other project that I'm closely involved in is the development of LISA S in collaboration with the Technical University in Delft. The LISA S is just the brain electronics, so just the pure autopilot of a UAV. I designed it to be as small as possible, making the size of a medium postage stamp, about 2 by 2 centimeters. It contains the 10 degrees of measurement sensors, a powerful ARM microcontroller with 0.5 megabyte of flash, as well as a GPS receiver module, while weighing only 2.5 grams. I have it here on the stage with me, so maybe it will be even smaller. Yeah. So, just like Crazyfly, I also developed a custom radio. The main reason was to save some more space and weight. The difference between Superbit RF and Crazyfly solution is the compatibility with the Spectrum RC control system. This solution allows us to have telemetry with the laptop computer or tablet and a standard model aircraft controller at the same time using only one module on the aircraft. Normally, these two channels are implemented using two separate radio systems. The initial motivation was an autopilot for a low-cost micro-helicopter airframes, as a retrofit solution providing additionally to the standard 10-DOM also a GPS receiver module, making it a perfect fully autonomous, for fully autonomous flights. And because it is just the pure brain part of the system, it makes it easy to mount on other airframe types too, like quadrocopters or airplanes, like these tiny things from China, for example. So you can just retrofit it with the board, and you should be able to fly autonomously with it. As I mentioned, we mounted a GPS on the Lisa S, making it useful for outdoor applications. It is still not quite accurate as we would like. But thanks to companies like Swift Navigation, we will be getting sub-1000 RTK GPS systems that will provide a centimeter accuracy at 50 Hertz. This is quite an improvement from current GPS solutions that provide best case accuracy of 3 meters at 10 Hertz. This is a significant step forward for outdoor applications. For example, small separation swarms where you fly the aircraft really close to each other and you can draw things in air with them, for example. Or fully autonomous aerobatic flight, because this module also supports really high accelerations, what you have big problems with commercial modules. Or this is also a commercial module, but the modules that you can currently buy on the market. Or precision farming, mapping, and so on. But what about indoor applications? Sadly, indoor autonomous flight is still very, very challenging. There are some solutions available, mostly for research groups that with really, really deep pockets. For example, infrared camera tracking systems. These are the same systems used to capture the motion of actors for 3D movies, like Gollum from Hobbit, for example. They're great, very accurate and fast. Thanks to the solutions like this, groups like GRASP at Pennsylvania University and IDSC at ETH Zurich can create incredibly amazing demos. I bet you have seen their videos of swarm flight, snapped-optimized flight planning, or ball-juggling quadrocopters. The problem is that an infrared tracking system like this is very expensive. And because of this, out of reach or even the very rich hobbyists or less wealthy universities. Besides the cost, one has to dedicate a room for the micro UAV in order to mount the cameras in the room at very accurate positions. You can't just go with your drone anywhere and perform autonomous flight, so I'm throwing it out there. We need to work on some solutions that we will have the following feature set. High accuracy, relatively cheap, no environment modification needed, light and very small, low energy and computational requirements. There are many approaches to solving this problem. Maybe laser-based radar, maybe computer vision, who knows? There are some very promising technologies on the horizon. One of them comes from a company called Technical Illusions. They are developing a new kind of virtual reality 3D glasses. The thing in the middle of the glasses is a tiny cell phone camera connected to an FPGA. They also will make a metallized gate array version of it to bring down the cost in pieces as well as need of power. It can track a blinking infrared LED pattern at 100 frames per second, providing a sub-millimeter accurate position and rotation of the user's head. I'm looking forward to mounting one of those on a nanodrone. Another solution comes from TU Delft. It was released just a few days ago. It is a tiny stereoscopic vision module for their micro-flapping wing platform called Delphi. The system is based on the parallax effect of binocular vision, just like we humans and every animal with front-facing eye does. Using two cameras, this module can also see depth, not only a flat image. It is not a totally new concept. What is the size. As you can see, it is pretty small and thus light. It can detect obstacles, and according to MATLAB, it is also quite affordable. It enables the Delphi to navigate autonomously. Definitely the videos look very promising. So here is like a time-lapse recording of the position of the aircraft, how it is flying in a room completely with no human control input. I think we are almost out of time, so let me leave you with a thought. In the world of PC software, we know about continuous integration, coding standards, static code tests, and so on. It is really hard to for embedded systems, and thus for all drone toys. I know many projects out there do software compilation tests and static code analysis on their software. But something I know we should work on is better reliability testing and for flight software we put on our toys. I know this will not happen overnight, but it is something we should make a priority of. I know this is not as much fun as flying them or developing new algorithms, but it would be a huge benefit, not only in this field, but other embedded system areas, to be able to do better regression and reliability testing. I know of the fact that there are some approaches provided as part of commercial development packages. What we need, though, are open source solutions for automated regression and unit testing tools for embedded systems.
Yeah, it's just using a whole bunch of streaming real-time things that it would go. I think you'll be hearing more about those in some states. Jason.
You can't offset.